Hello everyone, welcome to this lecture on Introduction to Boolean Algebra and Logic Gates. So I have prepared this video summary of the past three videos. So if you have missed it to watch the past three videos, this video will help you to understand it better. Or even if you have doubts with respect to previous three videos, watch this video, you will understand it better. So in this lecture, we will explore one of the most important foundations of digital electronics and computer engineering. Every digital device that we use today, including computers, smartphones, calculators, smart televisions, communication systems, embedded controllers, all these are operated using digital logic. At the heart of digital logic lies Boolean algebra. Boolean algebra is a mathematical system that deals with variables that can take only two values, 0 and 1. So these values represent logical conditions such as false and true, off and on, low and high, or open or closed. In this lecture, we will learn about formal logic, Boolean variables, Boolean functions, truth table, logic gates, fundamental laws of Boolean algebra, simplification techniques, and De Morgan's theorem. By the end of this lecture, you will understand how digital circuits are represented and simplified using Boolean expressions. Let's begin our lecture into the world of digital logic. So before learning Boolean algebra, you must understand formal logic. A statement, also known as a proposition, is a declarative sentence that is either true or false. So there is no intermediate possibilities. The statement, also known as a proposition, is a declarative sentence that is either true or false. So there is no intermediate possibilities. Consider the following examples. The earth revolves around the sun. This statement is true. A triangle has four sides. This statement is false. So computers and digital systems cannot understand this natural language. Instead, they represent information using binary values. So true is represented by 1, false is represented by 0. When a computer processes information, it continuously evaluates logical conditions and makes decisions based on these binary values. This concept forms the basics of digital computing. Every program that runs on a computer ultimately gets converted into millions of logical operations involving only zeros and ones. Formal logic therefore acts as a bridge between human and reasoning and machine computation. So a Boolean variable is a variable that can take only two possible values. These values are 0 representing false, 1 representing true. Unlike mathematical variables that can have many possible values, Boolean variables are restricted to these two states. So examples include a switch can be on or off, a lamp can be glowing or not glowing, a sensor can detect an object or not detect it, a door can open or close. In digital electronics, these physical conditions are mapped into binary values. For example, if a switch is on, we may represent it using 1. If a switch is off, we may represent it using 0. Boolean variables are the basic building blocks used in designing logic circuits and digital systems. Without Boolean variables, it would not be possible to represent logical decisions electronically. Boolean functions and truth tables. First, we will see the Boolean function. A Boolean function is a mapping from Boolean input variables to a Boolean output value. For example, f equal to a plus b. Here the output f, capital F, depends on the values of capital A and capital B. To understand how the output changes for different input combinations, we use the truth table. A truth table lists all possible input combinations and the corresponding output values. For two variables A and B, there are four combinations 0, 0, 0, 1, 1, 0, 1, 1. Truth tables are extremely important because they completely describe the behavior of a logic function. Whenever the engineers design a digital system, they first create truth tables to verify that the logic behaves correctly under all possible conditions. Truth table serves as a foundation for analysis, verification, testing, and implementation. Boolean algebra is the mathematical framework used to analyze and manipulate binary variables and logical operations. Using Boolean algebra, engineers can simplify complex expressions and reduce hardware requirements. A logic diagram is a graphical representation of Boolean expressions using logic gate symbols. So instead of looking at lengthy algebraic equations, engineers can visualize circuits using logic diagrams. So the logic diagrams help us to understand input, output, signal flow, and logical relationships. As digital systems become larger and more complex, logic diagrams become essential design tools. They allow engineers to convert mathematical expressions to practical electronic circuits. So logic gates are electronic devices used to implement Boolean operations. The three fundamental logic gates are AND, OR, NOT. The AND gate produces a logic 1 when all inputs are 1, only when all inputs are 1. The OR gate produces a logic 1 when at least one input is 1. The NOT gate inverts its input. If input is 1, output becomes 0. If input is 0, the output becomes 1. These basic gates are building blocks from which every digital system is created. Whether it is a simple calculator or modern microprocessor containing billions of transistors, all digital circuits are ultimately constructed using combination of logic gates. Boolean algebra contains several fundamental identities. So first, these comes under postulates and basic identities. First, let us examine identities involve 0 and 1. X plus 0 equal to x. Adding 0 to variable does not change the variable. X into 1 equal to x. Multiplying by 1 doesn't change the variable. X plus 1 equal to 1. If one input of an OR operation is 1, the output is always 1. X into 0 equal to 0. If one input of an AND operation is 0, the output is always 0. So these identities simplify the digital expressions and reduce the circuit complexity. Now let us discuss complements and idempotent laws. Every Boolean variable has a complement. If x equals 1, then x prime equals 0. If x equals 0, then x prime equals 1. So important identities include x plus x prime equal to 1, x plus x into x prime equal to 0. These relationships are called complement laws. We also have x plus x equal to x, x into x equal to x. These are known as idempotent laws. So these laws remove redundant terms and play a major role in algebraic simplification. Next is commutative law. So the commutative law states that the order of the variable doesn't affect the result. For OR operations, x plus y equal to y plus x, and for an AND operation, xy equal to yx. So this property gives us flexibility during simplification. Variables may be rearranged without changing the circuit functionality. Associative law. The associative law states that grouping does not affect the result. Examples: x plus bracket of y plus z equal to bracket x plus y plus z. X into y z equal to xy into z. So this rule is extremely useful when simplifying large Boolean expressions containing many variables. Distributive law. So the distributive law is one of the most powerful tools in Boolean algebra. X into y plus z equal to xy plus xz. Another Boolean specific form is x plus y z equal to x plus y into x plus z. So these laws allows us to expand and factor expressions depending on which form simplifies the design. De Morgan theorem. So De Morgan's theorem is among the most frequently used concepts in digital electronics. So the first theorem states x plus y the whole bar equal to x bar y bar. The second theorem states x plus xy the whole bar equal to x bar plus y bar. A rule to remember is change R to AND AND to R. Complement every variable. This theorem helps transform logic circuits and is especially useful when working with NAND or NOR gates. So generalized De Morgan theorem, and it is involution x bar the whole bar equal to x. Next we'll move to the function minimization. So these functional minimizations I have already discussed in the previous lecture. So you can I just write out the example, and laws used, I will just give the clue and laws used for this minimization. So for first one you can go for factoring, so that you will get the final result, and for the second one you can use the expanding and simplification, and for the third one you can expand and simplify, and fourth one also you can expand and simplify. So for expanding and simplification, we try to apply the Boolean algebra theorems that we have studied so far. Now we will go for one by one. Consider a into a plus b. Before that we have a plus b. Factoring a into 1 plus b. 1 plus b equals 1. So the result becomes a. A complex expression is reduced to single variable. So this means fewer logic gates, less power consumption and low implementation cost. Consider a into a plus b, expanding a plus ab. So a equal to a, we get a plus ab. So applying simplification, a into 1 plus b, result is a. So repeated application of identities helps reduce expressions significantly. So consider a plus a bar b, rewrite as a plus a bar into a plus b. So we have a plus a bar equal to 1, the result becomes a plus b. So this example demonstrates the power of complement laws in algebraic simplification. Next one is a into a bar plus b, expanding a bar plus ab. Since a bar equal to 0, the result becomes ab. The final expression requires much less hardware. Let us simplify ABC plus ABC bar plus A bar C. Taking common terms from the first two expressions, AB into C plus C bar. Since C plus C bar equal to 1, the result becomes AB plus A bar C. The three terms have been reduced to two simpler terms. So so that AB plus AB bar equal to A. That is one. So taking a common factor a into b plus b bar, since b plus b bar equal to 1, result equal to a. The proof is commonly used in digital circuit analysis. So like this we have to prove. Another one, a plus b into a plus b bar. So after expansion and simplification, the result becomes a. So we have learned so far formal logic, Boolean variables, truth table, logic gates, basic identities, complement laws, commutative, associative and distributive properties, De Morgan theorem, function minimization, Boolean proofs and simplification techniques. Now let us take some time to understand why De Morgan theorem is so important in digital electronics. So many students initially memorize the theorem without understanding its practical significance. However, De Morgan theorem is actually one of the most frequently used tools in circuit design because it allows engineers to transform one logic implementation into another without changing the final output. For example, suppose a designer has created a circuit using AND gates and OR gates. During manufacturing, it may become more economical to implement the same circuit using only NAND gates. So at this point, De Morgan's theorem has become extremely useful because it provides the mathematical relationship needed to convert expressions between equivalent forms. So let us consider a plus b the whole bar. According to De Morgan's theorem, this becomes a bar b bar. So notice two changes occur simultaneously. First, the OR operation changes into AND operation. Second, each variable receives complement. Similarly, if we have a bar plus b bar, it becomes again the AND operation changes into OR operation and each variable is complemented. So a simple way to remember this theorem is to imagine that the complement sign pushes inward through the expression. Whenever it moves inward, it flips the operation from AND to OR, from OR to AND. So this visualization makes complex simplification much easier. So engineers regularly apply this theorem when designing processors, memory circuits, communication systems, control systems, and embedded applications. Therefore, mastering De Morgan's theorem is essential for anyone studying digital electronics. So now let us discuss why functional minimization. Why this kind of functional minimization is such an important topic in digital design. Imagine that two engineers are asked to build exactly the same logical function. So the first engineer implements the expression directly without simplification and uses 10 logic gates. The second engineer applies Boolean algebra and reduces the expression before implementation. So as a result, only 5 gates are required. So both circuits can produce the same output, but the second circuit is clearly superior. Why? First, fewer gates mean lower manufacturing cost. Second, fewer components mean reduced power consumption. Third, a smaller circuit occupies less chip area. Fourth, fewer gates result in lower propagation delay, which increases speed. Finally, simplified circuits are usually more reliable when there are fewer components that can potentially fail. So these benefits become even more significant in modern processors that contain billions of transistors. Even a small percentage reduction in logic complexity can save considerable silicon area and power consumption. So that is why Boolean simplification remains an essential step before any digital circuit is manufactured. So now let us discuss some practical applications of Boolean algebra. So before we conclude, let us explore where Boolean algebra is used in the real world. First, and perhaps most obvious application is inside computers and microprocessors. Whenever a processor performs an arithmetic operation, evaluates a condition, or executes an instruction, Boolean logic is involved. Boolean algebra is also used extensively in communication systems. When data is transmitted through a network, various digital circuits perform encoding, decoding, error detection, error correction using logical operations. Another major application is embedded systems. So devices such as washing machines, microwave ovens, smart televisions, automotive controllers rely on digital circuits designed using Boolean algebra and Boolean principles. Industrial automation systems also depend heavily on Boolean logic. For example, consider a factory conveyor belt. A motor may run only if power is available, safety switches are active, and emergency stop condition is absent. Such decision-making process can be represented using Boolean expressions and implemented with logic gates. So Boolean algebra is a fundamental to robotics, medical electronics, aerospace systems, and artificial intelligence hardware. So in short, almost every modern electronic prompt around us relies on Boolean algebra in some form. So let us summarize everything we have learned in this lecture. So we began by understanding formal logic, right? And the concept of statements that can be either true or false. We then introduced Boolean variables, which are restricted to binary values of 0 and 1. Next, we studied Boolean functions and truth tables, which help describe logical behavior for all possible input combinations. We also learned about logic diagrams and basic logic gates used to construct digital systems. We then explored the fundamental laws and identities of Boolean algebra, including component complement laws, commutative laws, associative laws, distributive laws. These identities form the toolbox used for simplifying complex expressions. Afterward, we discussed De Morgan's theorem in detail and saw how it enables conversion between equivalent logical forms. We also examined several worked examples demonstrating how Boolean expressions can be reduced systematically. So finally, we learned that simplification is not merely a mathematical exercise. It directly influences circuit speed, circuit size, circuit cost, power consumption, and reliability. Boolean algebra is therefore much more than a set of equations. It is a language used to design and optimize the digital world around us. So as you continue studying digital electronics, these concepts will serve as the foundation for logic design, K-maps, corner maps, combinational circuits, sequential circuits, programmable devices, and computer architecture. So that's all. Thank you for your kind attention, and I look forward to have doubt clarification in the chat. So these additional content are very much useful for you to apply the concepts in real world applications. So try to answer for the quiz posted in the Scout LMS, which is also available in the chat box. So which help you to understand more detail about Boolean algebra. So thank you for watching this lecture. Have a good day.